Hello everyone, welcome back to Structure Spurt. Today I'm really excited to show you a new project, steel structure. This is a very simple structure. It's not a golden bridge in Vietnam or the longest bridge in the world, but it's a small bridge like this one. Now let's see it. Yes, it is the composite walkway steel bridge over the road. Now let's take a look to architectural plan. This is the option 1. Yes, there are 2 or 3 options in the model. Now we select this one, the last model. The overall span center to center of column is 14.5 meter. 14.5 meter. 3D architectural plan. Now let me ask you one question. How do we design steel composite walkway? What is the design control on the project? The ultimate limit state, the strength of the section, the deflection, or the local buckling or pressure buckling or lateral torsional buckling that control this design. Now let's jump into the deep about this tutorial. You will know how to design and how to control and how to check this model. Okay. For the architectural plan, yes, the architectural plan. So we need to model and design it in Etabs. Etabs is not professional for design bridge structure, but we can do it in case we don't have other professional software like CSI bridge. So let's start with the Etabs. Okay. The easy way to model the complete structure or the any shape or complete shape in the architectural model, we have to model it as the element and export as DES file import to Etabs. Now let's start. Like this one, just throw it in the AutoCAD. Now let me click and check for the the layer steel beam, and layer for the concrete column. After we complete for modeling in the AutoCAD, you can see it as the DES file. Now let me see it and select the version of DES file. Okay. After that, you can import it to the Etabs, just like this one. After we complete import model, just click import architectural. Again, import the files or architectural plans. Okay, and select open. That's all. After we complete for the model, now let's jump to the analysis in design. I show you the section. You can start from the pre-trial. We don't know exactly the section can design past this requirement, but we try to fit it step by step from one step to the second step, third step, and so we can fit the problem, the section. Now this is the final section I designed. Again, sign, clear display all signs. Okay. The main beam is IPE 600 and the secondary beam is IPE 120. And for the concrete column, C 1000 millimeter. 1000 millimeter. Okay, so we can design and optimize the section later. Now we can start the concept for design this structure. So we should understand about the steel structure, composite structure, and OC structure. We design it as the simplest supporting beam for the main girder or main steel beam, and we use the secondary beam spacing. You can select for the first free trial section and free trial spacing. This is the final line I have analysis and design. So the spacing is more closer for the section IPE 120. You can increase the spacing by increase the section or IPE to 150 or 120. Okay. Now let's click on the floor to make sure you assign it separately. Okay, this is the main beam, and we design it as composite beam. Now let me click on the plane one. Okay, select type. I select on the beam. Okay, on the beam we select all the beam and design. Now let me check. Yes, click on design, click on override frame design procedure to make sure you select all the steel beam design it as composite structure. Okay, composite, and click it's okay. In some cases the steel beam is not designed as composite. In the default, after you assign the floor on the steel beam, it designed it as the steel structure. So to make sure this structure is a composite structure, now let's select on the composite steel beam and click OK. If you do not want to design this structure, this selected element, so you can choose to no design. But in the default, to make sure in the default is correct for the composite. Now click on the composite. Okay, and check for the designs. Steel section, steel deck 1, and check for the grade of the deck and grade of the material and the section. Okay, and load combination. We add the load combination automatically into the default. You can use the menu design input one by one, or use the default. Just click on the design composite and convert to editable. So you can edit the name. Click OK. It's all. And now let's start this one. I can create a copy from the did load plus line load. We want to verify the deflection of the did load plus 10% of the line load to verify with the frequency. We do not check the frequency of the did load plus full line load. So we only check for the did load plus 10% of the line load. For the floor vibration, to control floor vibration, this is the load combination we must to check. Did load plus 0.1 line load. Modify. Okay, it's correct. Okay. Okay. Now let me continue to analysis. You can set degree of freedom or advanced sapphire option. Okay, now let's run analysis. No case to run because I ran it already. Just unlock the key and click on run analysis again, or you can press F5. Okay, the shortcut is F5. and click on the rotate 3D view. Start animation. Animation also important to check the connectivity of the member to make sure the member and the floor is connected together. Okay, everything is fine. Now let me click on the stop animation and click on the plane. You can view on the floor plan, or you can view it at the perspective view, and click on the moment. Now let me check for the ultimate limit state, the ultimate load combination, the load plus the light load, the moment about the measure axis 33, or you can check in plane or out of plane. Yes, in plane or out of plane, sorry. Okay, 3. Okay, now let me check the 33. You see the maximum moment is 355.4305 kilonewton meter, and at the side beam is 219.58. Yes, it's similar. Okay, you can check for the shear M22. Yes, for the shear, we assign this beam as a simply supported. We design it as simply supported beam. The simply supported beam, the friction is maximum at the center, and the shear is maximum at the support, and the moment is maximum also at the center of the beam. So to ensure all the structure is the same with your concept, you want to design the steel structure as a simply supported or as the fixed support. For the composite structure, I choose the simply supported. Okay, click OK. For the deflection, you can check at the load plus light load, but okay, now let me check the load plus light load. Let's start from assign, clear assign, and again we come to the show deform shape or press Escape. Okay, combination, and we choose the load plus light load. Apply. Okay, now let me grow over the beam. See the maximum deflection is 23.51. Okay, 23. Okay, this one is 23.51. And the total length, yeah, the span length is 14.5. Now let's check quickly. Sorry, I just opened the blank sheet. It's there. Okay, this is the blank sheet. Now take a quick check for tint. 14.5, yeah, divided 360, or you can increase it, change it to the millimeter. The maximum deflection is 40.27 millimeter. And now let me check to the Etabs. The maximum deflection is 22.21, so it's acceptable. Yeah, 23. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23.21. 23 Okay, now let me run up to 23. And a low ball. Allow web ball deflection. Allow web ball deflection. This is the analysis deflection. Analysis in Etabs. Deflection in Etabs. For the deflection is acceptable. Now what is the main issue when you design for the long span structure, especially for the steel structure and live structure? The design control, you can check step from one step to other step. You can check for the moment, the resistance of the cross section, the deflection, and other one criteria is very important, cannot be ignored, is the floor vibration. I just told you it is very important, floor vibration. Again and again, listen to me carefully. Yes, now let me check other criteria. Is the dead load plus 10% of the light load for verify floor deflection, floor vibration. Okay, click again. Now let me check all the deflection. It's 14.18. Yeah, now let me take this one. 14.18. Okay. 14.18. And for the lower ball floor vibration, the simple formula is 18 over the deflection, dead load plus 10% of the light load. So over this deflection value. No square, sorry, square root, not absolute value, square root or the, sorry again, square root. Okay, so this unit is hertz. The allowable unit, the allowable frequency on the floor is from 4 Hz to 10 Hz, or from 4 Hz to 8 Hz, generally in range of 4 to 8 Hz. So this structure is acceptable for floor vibration. You see here, in the case you increase the deflection. Now let me increase deflection to 20. You see the frequency is lower and even lower. Now let me change to the 40, the deflection. You see here the floor vibration is very low. It's 2.84 Hz. It's not acceptable. We prevent resonance on the floor or the structure to make sure everything is acceptable. To confirm the acceptance criteria, let me change to 40. Sorry. You see here, if we increase no, sorry. Now let me increase it, the ball is 40. So the floor vibration is unacceptable. It's lower than the low ball floor vibration in range 4 Hz to 8 Hz. Generally 4 Hz to 8 Hz or 4 Hz to 10 Hz. To prevent resonance on the structure, it not acceptable. Now to make sure in some case the deflection is acceptable but flow vibration is not acceptable. Okay, now let me come back. Okay, 823 2020. Now let me change it to 20, and this one I assume it's 35. You see here in this case the deflection is acceptable but flow vibration is not acceptable. The deflection is also a function with flow vibration. To control flow vibration on the floor, you should control deflection. Okay, to decrease deflection to 20. Now 23. Everything is not okay. Yes, this one is okay. So you want to control the deflection. Also can control the flow vibration. For the long span structure, for the long span steel structure or lightweight structure, this is very important to check not only for the local buckling, lateral torsional buckling, or pressural buckling, or shear, or other criteria, but don't forget check flow vibration. I see a new designer or some designer always check only for the deflection, not check for the flow vibration. It is clear? Yes. Okay. Now let me come back to design and composite steel beam. Let me click on start design and check. And composite steel beam. Again, composite steel beam. Display design information. You can display design in the composite steel beam design data, stress ratio, deflection ratios, and bottom flange stress ratio, vibration ratio, and the shear start ratio. For the composite, you can verify with the vibration ratio. If you design in the steel beam, not include the option for vibration. This option is very good to verify to complete design for the composite structure. Okay, now let me check on the stress ratio design. Order. Yes, stress ratio. You can check for the stress, final load, or deflection to verify with the total loss. Yeah, again deflection is only 30%. Stress and vibration ratio. The vibration ratio is 0.76 and 0.31. And shear start ratio, yes, is very low. Click OK. Design, composite. Interactive design. And verify analysis and design section. Verify all member pass to make sure all the member pass not failure. Okay, all composite beams pass the design check. Okay, and again click on the design, composite beam design, composite beam design. Verify analysis visual design section. Okay, very fine, very good. Now let me click on the beam and right click to check the design, the analysis. IP is 600 and the design ratio is 0.331. Yes, 0.331. Now let me check the design ratio. Come back to the moment M33, change the combination to the ultimate load combination, and the maximum moment is 355.3.43. okay, now let input to my it. I select the section to IPE 600. You can change the section, and the steel grade 235 megapascal, and the section is IPE 600. The moment, we apply the moment, and input the C00 at the center. Okay, so the design ratio is 0.431. We input the length from the secondary beam to the secondary beam is 1 meter, so we input it at the restraint on the main beam. Okay, so you see here the design ratio is 0.31. Now let me check with the Etabs. Come back to design, composite beam design, display design info. You can check one. Yes. Now let's check the design control for the moment is 0.431, and for the vibration is 0.31 for the middle beam, and for the side beam. Now let me click again. The design for the moment is 0.26. It's 26%, but the flow vibration is the control of the design stage. The design stage is 0.26, is 26%. For the side beam, the design control is flow vibration. Okay, or vibration. And for the middle is the bending moment. Okay, as I verify in my Excel, it's similar. This Excel is not for the composite beam, it's for the steel beam. The result of Etabs design as a steel beam is not a composite. I just verify it. Okay, the analysis IPE 600. Okay, you see here everything is correct. We analyze it and verify with menu. Okay, continue to come back. Now let me click on the floor plan. Now I change the section of IPE and check what happened when I change the section IPE 600. Okay, now let me to assign select property frame section. I select IPE. Yes, select it all and replace it with the new section. Now I check the section. I want to use IPE 500. Okay. Okay. No, not change. Okay, again assign frame section IPE 450. Apply. Okay. Now let me check. I do not change other parameter. We just change the section and to verify it again. Now let's check the load. We apply the load 1.2 kilonewton per square meter, and the uniform load is 3.5 kilonewton. The load applied on the long span structure or on the bridge, you should consider the effect of dynamic on the floor. Okay, when you apply the static load on the floor, multiply with the dynamic factor to increase the load. Okay, and for the load arrangement also has a different style arrangement. Now let me show you some concept how we can arrange the load on the floor. Okay, skywalk, Etabs. Okay, the load distributed on the floor has a different options and can produce the maximum load on different location of the beam. Now let's start with the load distribution on the right side of the bridge. We assume it apply fully distributed on the right side. It can produce the maximum critical on the steel deck or on the structure by twisting or by reduce the torsion on the beam, or we can extend the distributed load to apply the fully distributed on the floor. So in the case the load is balance each other on the span to span, the span of the steel deck is 1.673 is the same. So in the case when we apply the full distributed load on the floor, we concern the maximum moment and shear force. Okay, so in the steel bridge we should apply in the different load pattern. Sometimes load pattern maximum on the left side or on the right side or on the middle of the bridge can produce different effect on the bridge. It is very simple. You can apply the moving load. I add dynamic factor, include this static load to increase the static load. To make sure you know about the dynamic effect on the long span structure, especially on the bridge structure. I hope you know that. You can check more about the dynamic effect on the structure, how to increase the load. Okay, now let me come back to the Etabs. Okay, now we change the section to IPE 450. Run it again. Okay, load. Yes, did load and line load. Run it again, run analysis. Or you can press shortcut F5. Okay, now let me click on the design and composite beam design. Yes, click on design. You see here now the ratio is 1.57. It's over 100%. This beam is not acceptable. You must to be change the section. And what is the design control on the section? We have to check it. So the secondary beam also fair and the main beam also fair. Okay, just click on this beam and right click to check. The bending moment is only 0.35. It's okay for the bending moment, but why this steel beam fail? You see here the walking acceleration is over, the floor vibration is over. The ratio is 1.57. The simple assessment for steel floors. The following design procedure is based on a parametric study of the wide variety of regular floor grids model using an approach and is suitable for composite floors. The design procedures for assessing the dynamic performance of floors comprise definition of natural frequency, definition of modal mass for the floors, evaluation of the response, take of the response again acceptance criteria. We are concerned about the fundamental frequencies and the formula for check the frequency S0 is equal to 18 over the small theta is the lead load multiplied with 10% of the line load, produce the deflection. Okay. So when the crowd or when the people walking on the floor can produce the vibration on the floor, and it is the walking acceleration. It is very important to control the floor vibration. You have to change it. You can change the system of the floor, or you can increase the section of the supporting member. Okay, now it's clear. The bending moment is acceptable is only 35%, but the floor vibration is unacceptable is 1.25, is 157%. Is not acceptable. Okay, so we have no choice. We must to follow all the criteria, not only for the bending, for the flexural buckling, or for lateral torsional buckling, but also for the floor vibration. Again, come back, design. Let me select property frame section. Now I come back, change from the 450. Now I want to change it to the 600. Okay, run analysis again. And click on composite, start design again. Okay, you see here the ratio is 76% and 71%. Okay, I hope you enjoyed this tutorial. I designed this steel composite beam in Etabs, verify with the Excel, and also verify floor vibration. Everyone should know what type of the structure you are designing. You design the long span structure, the road structure, or bridge structure, or composite structure, or OC structure. For the OC structure, floor vibration is not affect too much, but for the lightweight structure or for the composite steel, for the long span structure, you must be verified for the floor vibration. And with the deflection, sometimes deflection is control on the design, sometimes floor vibration is control on the design for the long span structure. You see, in the case, the moment is not control for the designation of the member, but it's the floor vibration. Okay, after you complete design for the steel member, you must to design for the steel connection. For the steel connection, I designed it in the idea statica. Now let's look at idea statica model. Yes, the model steel connection. Yeah, to make sure everything is past the requirement. And for other connection, we design it in the creative advanced design connection. Now let me check. Yes, for the top plane, Just take a look. For the steel connection, we use the moment connection designed at the maximum moment. Actually, we do not supply the connection at the maximum moment. We supply it in a different location. The maximum moment is the middle span, but we supply it in the segmenter. After segmenter, we supply it in the different segment. The segmenter is the one segment of the standard length of the beam. It can transport and easily transport from the steel warehouse to the construction site, and you can check the connection on the beam and connection detail on the girder connection. Okay, now let me check. Okay, this one is the detail main girder connection. You can issue this connection. As I told you, I designed it for the maximum at the middle span, but when we split the beam, it's not at the middle. We split it in the middle. Yeah, middle is the location, but we split it in the location. So the moment also issues is not maximum. Okay. The connection of the steel beam to the OC beam. This is the section of the composite floor. You can check composite floor. Thank you for your watching. I hope you enjoyed the tutorial. Now just take a look to the drawing. Thank you for your watching. I hope you enjoyed the tutorial. For more details, you can ask me in the comment, or you can ask me in the group. I will try to answer you. Thank you.